So I've got 11 people logged in so far. I'm gonna dawdle for a couple of minutes to see how many other ones show up. And where did you send it? Yeah, okay. All right, so I've got about 12 people, I think, so far. We are going to pick up with the portion of chapter 1, kind of where we left off. So let me pop open my notes so I can share screen with this. Which is being really flaky. Why is it doing this? There, okay. Okay, so this should be hopefully sharing the screen from where we left off, roughly. All right, so the last thing we were talking about was going from kilocalories to kilojoules. So that was one of our multi-step problems. One little additional bit that I want to just kind of go through, and it will pop up again later, is where it says extra info. These are things that where you are reading chemical equations, you will see them used as subscripts. So solid, liquid, gas in kind of obvious SLs and Gs. The one that you may not be familiar with is AQ, which is aqueous. Aqueous means dissolved in water. So I had inserted an example here, and I didn't realize till I popped open my file today, because I usually do this on the board. So I am going to do a different problem, and I'm going to see if I can use the whiteboard. I'm not certain exactly how this is going to work, but I'm going to take a stab at it. All right, so first of all, we're going to look at a picture. Phil has a rocket. Phil has a really big rocket, and he is carrying it across the field. We are going to calculate the momentum required to launch that rocket. All right, let me see if I can do the whiteboard thing. All right, this is supposed to be a whiteboard. We'll see if this actually works. Okay. So Phil has a rocket. And that rocket weighs 332.9 ounces. Okay. It clears the launch pad at 50 feet per second. We want to know, what is the momentum? Okay. One of the things we need to know about momentum is what the units are. This is a crossover between physics and chemistry. Momentum is kilograms times meters over seconds, okay? Because it's kilograms, which is your mass, and then you have to multiply it by your speed. We don't have a velocity because I don't have a vector. All right, so I'm gonna see if this will cooperate and I can show you how this problem works. I'm gonna do my conversion of my mass as my first option here. So 332.9 ounces. And I'm going to multiply by 1 pound is 16 ounces. Okay, that's going to give me a conversion over to pounds. So I get 20.8 pounds. And then I want to go a little further. I want to multiply that. Actually, let me see if I can drag my screen across there. Okay. I want to multiply that by the fact that 1 kilogram is 2.2 pounds. So I've linked together two different conversion units here. Okay. And ultimately, I should get 9.46 kilograms. So I'm partway there. That's one of the units that I need when I'm calculating momentum. So the next part, I have 50 feet per second. The per second part is actually not going to change. It's the 50 feet that I'm actually worried about here. So I'm going to do 50 feet per second. Oops. Per second. And I'm going to multiply that by 1 meter is 3.28 feet. So this is going to give me 15.2 meters per second. So I got one more step in this deal. So I've got a mass and I've got a speed. I need to actually multiply them together in order to find my final value. So the 9.46, which is kilograms, I'm going to multiply that by my 15.2 meters per second. And that will give me 143.79 kilograms dot meters per second. Okay, so that should be your final answer for that problem. Like I said, this one's not included actually in the notes because I had kind of a brain glitch. However, this is obviously being recorded, so I will have a, you can go back and look at it again on the recording if you want to go back and view the example again. And somebody sent me email regarding not being able to log in. Let me see if I can solve this. All right, maybe that'll solve that problem. Okay, so let me go stop share again. Okay, so questions about dimensional analysis before we move on to the latter section of this chapter. Any obvious questions about the dimensional analysis parts?
So everywhere on homework, whenever we see feet, gallons, anything, we're gonna turn it into C system, right?
It depends upon what the question asks for, but yes, typically we are converting from standard American English units over to metric units for most of the problems.
But we got on homework exercise 5, and here's the feet, here are the gallons, and here's the miles. So I don't know which one to use. Feet.
So because I gave you in number 5, I gave you feet, I gave you time, I gave you how big the tank is. Okay. The ultimate answer should be how far can you go in an hour? So you are going to have to do a number of different conversions in order to get miles per hour, because the answer says how many hours will the journey take. So basically you're figuring out how far you can go on a single tank of fuel. So you have to have miles per hour to make that work. You also have to know your 8 miles for every gallon. So I gave you all of the standard things that you actually need in order to do that calculation. I didn't tell you how many seconds are in an hour, and I didn't tell you how many feet are in a mile, but I gave you all the rest of the information. The other bits you can look up because it's homework.
I turned everything into feet, and I counted into feet.
You could do it that way.
But actually in C system, it's in meters, right?
Yeah, but I didn't give you that, and I didn't ask you for that either. Dimensional analysis is just from a unit to a unit. It actually doesn't require you to go between different systems. It's just from a unit to a unit. It could be furlongs per fortnight, and that's still a valid unit.
Yeah, but to plug it into formula, we have to use either feet or either miles.
You need to know how many feet are in a mile.
So we use feet.
Yes, you're going to need feet to do the problem.
So we convert it into feet, count everything, and then turn it into mile because the answer is supposed to be in miles.
Yes.
So, okay.
It's a multi-step problem. It's designed to be a little messier than a lot of the standard problems. That one has several steps to it.
In our homework, do we have like an examples of the problems that we have? Like, for instance,
there are examples in the textbook. There's also a couple of examples in the notes, and the additional example that I just did on the whiteboard. Like I said, you can go back and review that by looking at the recording later if you want to go back and have another look at it.
Okay, all right. Cool.
Any other questions?
Yeah, real quick. I'm sorry, I'm joining just a little bit late. I was on the wrong Zoom.
Okay.
So the answers for number 5 with the dirigible is was it 2,000 miles in 7 to 8 hours?
So okay, so I gave you a certain amount of information. So I gave you that we want 450 feet per 12 seconds. It is a 250 gallon tank, and it gets horrible gas mileage. It takes a gallon to go 8 miles. So if you have those two pieces of data and you know how fast you are going, because you're going to have to convert it over to miles per hour, and you're going to have to convert feet into miles in order to make this work, you should ultimately be able to figure out.
How many miles you get in your answer? 2,000?
Yeah, I got 2,000.
And our 78.2?
No.
Okay, I got 78.2.
I got 78 hours. Don't know if that's right.
All right.
I will go through answer keys to the homework after because homework is probably going to be due on Thursday if we actually get through the end of the chapter today. So over the weekend after you have submitted your homework, I will post answer keys, and then next Tuesday I'll actually go through it and we'll talk about all the mechanisms for the answers.
Oh, this wasn't due Sunday?
No, we haven't finished the chapter yet.
Oh, I thought it was due Sunday. My bad. Well,
No,
it's already in.
chapter homework is not due until after we finish the chapter.
Oh, well, I guess I'm ahead.
I have a question.
Yes.
I guess it's about the same question that they were already asking about. Are we expected to continue with the significant digits through number 5?
That particular question did not specify sig figs.
Correct.
So I am more interested in that you do the math correctly for that particular problem.
Okay. So we can assume that if it doesn't say anything about significant figures, that we don't have to think
Right.
about
Then
significant
my
digits?
focus is actually on the mathematical steps and not actually on the sig figs.
Awesome. Thank you.
Other questions regarding that? All right, we are going to pop back over to hopefully my note bit here so we can talk some more about that. Where is my file? There. All right, so we are going to jump over to temperature. So, okay, if you start at the middle school end of things, if you ask somebody who's in middle school, it's like, so what's temperature? They're probably going to tell you it's how hot or how cold something is. We want to do this a little bit more abstractly, in part because it makes a bigger difference when we get to the thermochem chapter. So we're going to say that temperature is a measure of the average kinetic energies of the particles in the sample, because that way temperature is not actually dependent on the scale that you're using, because there's three different scales that we use in chemistry, one of which we don't use a lot of because Fahrenheit is not really chemistry. There are some other temperature scales that are used by the engineering people. You might run across them in other places, but we are not going to particularly deal with them for this semester. So we've got Fahrenheit, Celsius, and Kelvin. Oh, right here in the US, unlike the rest of the world, we're sort of stuck in the Fahrenheit version. To give you sort of a mental peg to hang your information on, we're all familiar with water freezing. If we compare those three different units, so it's 32 if you're in Fahrenheit, it's 0 if you're in Celsius, it's 273 if you're in Kelvin. So then how about the other big benchmark in the world of temperatures, which is water boiling? Has a really odd number, 212. It's like, how did they get that number? But anyway, that's what we're stuck with. 100 Celsius or 373 on the Kelvin scale. So as you can see there, I gave you just a little snippet of info that kind of goes with this. Celsius was actually a watchmaker. He constructed a tube that he filled with mercury, and he engraved in this long spiral 100 equal units. I actually don't know. I don't have on the tip of my tongue the Fahrenheit tale, but it was different. Kelvin, we're actually going to hear about Kelvin again. He was an important dude. Kelvin is actually his title, not his name. His name is William Thompson. British nobility, you know, like all these dead white guys, who was known as Lord Kelvin. He's the one that the SI unit is actually named after. Going back and forth between Celsius and Kelvin is actually pretty straightforward, and I did a little bit of rounding. Okay, if you actually look up the nitty-gritty details of Celsius and Kelvin, you will often see that some of the textbooks will quote 273.15. Okay, most physics and chemistry textbooks have a tendency to round for the purpose of doing problems. And we're going to just use the 273 flat and not worry about the 0.15. So if you want Kelvin, you started with Celsius, add 273. If you want Celsius and you started with Kelvin, subtract 273. And I gave you an example, and I think there's an example in textbook too. I had 90 Celsius, haven't quite reached boiling. If I add 273, I get 363 Kelvin. Going back and forth between the Celsius and the Fahrenheit, yeah, that's a bit messier. Now, there's two different ways to approach this. I used the fractional version, the 9/5 and 5/9. There is another variant on this that makes it a decimal, 1.8. 1.8 is 9/5 anyway. If you learned it using the 1.8 version in another class, high school physics or chemistry or you know, whatever you had before, that's okay. It'll give you the same answers as long as you use the math correctly. So if I want Fahrenheit and I have Celsius, I need to do this in 2 steps. And the parentheses make a very specific difference. I need to multiply by my 9/5 before I add the 32. So 38 times 9/5 gives you 68.4. Then add your 32, and so Fahrenheit will be 100.4. Now, one of the things that I also do, because this is tied into the equipment that we use in lab, the thermometers that we use in lab, and there are 2 different kinds. There are the oh so cheap $3 ones that are filled with alcohol that have the red coloring in the middle. Those, if you're lucky, you can kind of estimate to the nearest 10th. We also have some digital thermometers, but they're not really like super expensive ones, and they only go to 1 decimal place. So I have a tendency, from this sort of realism of trying to tie this into lab, that a lot of times, even if there's a couple of extra digits in the decimal place area, I will go ahead and round to a single decimal place, because that gives us kind of a good feel for what we're going to experience when we do temperature measurements in lab. So how about going in the opposite direction? So here in the US, 350 Fahrenheit is a really common, I'm going to bake something in the oven temperature. So how about Celsius? Now this one has the parentheses in a different place. This one requires you to do the subtraction part first and then use your fraction. So 350 minus 32, you see we get 318, then multiply by your 5/9. And also this one I only just carried to a single decimal place. We've got 176.7. Now what if you had to go 2 steps? Okay, this is something that is not uncommon, especially for some later chapters. You may see some usage of this. What if you wanted to go from Fahrenheit all the way to Kelvin? Got to do it in 2 separate steps. Worry about your Fahrenheit to Celsius conversion first. So this one, I did my 106. I subtracted 32. That gave me 74. I multiplied by 5/9. I get 41.1 Celsius. Then add your 273. So ultimately, you get 314.1 Kelvin. Now remember that this is a chapter that bounces around a lot. This is a chapter that has a whole bunch of different topics in it. Density is one of those. The people who were in lab last night got to do this hands-on. The people who have lab 2 weeks from now, my Monday people who have lab 2 weeks from now, will get to do it then. Density is basically a ratio. Density is mass per volume. Now, chemistry physics point of view, the ones that you are most likely to see are grams per milliliter or grams per cubic centimeter. Both are actually the same thing because 1 milliliter is 1 cubic centimeter. However, I will say that liquids are often reported with the milliliter as the bottom unit, whereas solids are often reported with the cubic centimeter. I think in part because if somebody gave you a brick, okay, you could measure the 3 dimensions and calculate it up in cubic centimeters, and that would be really straightforward that way. So I think that's kind of why we tend to lean in that direction. So some more tips. Reality checks again. It is highly, highly unlikely for anything that you are doing in general chem that you will see densities higher than 30. Osmium, the element with the symbol OS, has a density of about 28.5 grams per cubic centimeter. Osmium tetroxide, which is kind of a slang thing, it's not actually technically the correct name for it, is used in electron microscopy. And part of the reason it's used is because it is very, very dense. Now, if you ever take theoretical physics or astrophysics, things like neutron stars and things like that, yeah, you might see numbers above 30, but for general chemistry stuff, especially things that we are likely to do in the lab, you're definitely not going to see anything above 30. Yeah, I've seen some homework answers where people have told me things like what I wrote there in my notes of, oh, the density of my sample was 422 grams per milliliter. I'm thinking, yeah, that would like sink to the center of the earth. So keep that in mind when you're actually doing the math part. All right, since this particular equation has 3 parts to it, the D, the M, and the V, you got to be able to solve for all 3. So I decided to give you one straightforward usage as the first one. If you have a liquid, you know its mass is 43. You know its volume is 39.5. That one's a really standard. Put the D, put the M on the top, put the V on the bottom, divide. You get 1.09 grams per milliliter. What about gases? Okay, gases we do know are a lot less dense than liquids and solids. Technically, you're supposed to actually have some additional information here. Technically, you should know temperatures and pressures, but I'm giving you the simpler version for this particular example. It's a lot less than 1, okay? 0.0021 grams per milliliter. I have a sample. It's 1.6 grams. If I put my numbers in, okay, put them into the equation first. So 0022, oh, I have another glitch. Okay, there's too many twos in that example. I realize that. It's supposed to be, and it's right on the bottom, it's right in the next line, but I actually hit two twice apparently. Okay, so 0021 is what it's supposed to say. Equals 1.6 over V. Think about your algebraic rearrange. Anything that is on the top on the left-hand side can be swapped with the bottom on the right-hand side if there's an equals in between. So I flip-flopped it. I get 1.6 divided by 0021. And I have a volume of 761.9, or if I round it just a little bit, I get 762 milliliters. One more thing you need to be able to solve for. The mass. So I have a chunk of metal. I actually know the density of this chunk of metal. It's 10 and a half. I have volume for it, 18.2. Again, this is kind of plug and chug. Put in your density, 10 and a half. Put your 18.2 on the bottom of the opposite side. You can bring it up and multiply, because if you bring it up to the other side, you can multiply your two things together, and this will allow your grams to cancel out. So I get a mass of, actually, it's all your milliliters to cancel out, not your grams. And that will give me 191.1 grams. And that actually, I think, gets us all the way to the end of this chapter. So, as I suspected, homework then for chapter 1 will be due on Thursday. I know that a couple people sent it to me already, which is fine. I'm actually not going to grade it till this weekend. But you should turn it, you should do the submit, do your file, do your save. When you put it in through the Canvas system and it asks you to submit, attach your file. And I will open them to grade this weekend. And eventually I will post the grades. And then on Tuesday, a week from now, I will go over the answer key. So it's probably Friday, after everybody's turned in their homework, I will post the answer key so you can at least look at it over the week, over our long weekend. And then I will go through the answer key on Tuesday, so that people have ideas on where they might have gone wrong. Questions about chapter 1 information? All right, we are gonna jump chapters then. It's gonna take me a couple of minutes here to pull up my other file. All of these are already loaded to Canvas. I think I loaded all the way up through chapter 5. Which still leaves us like 3 more chapters that I haven't done the loads for yet. But I'm trying to keep ahead so that if people need to print stuff off if they want to, that they can go ahead and deal with that. All right, so let me find my document for chapter 2. All right. So, and yeah, I'm kind of honest about this. There's a little bit of stuff here that's actually not in the textbook, mostly because it's background, and I didn't update my number either. Technically speaking, there are more than 111 that officially have names now. I think number 115 and 116 actually have names now, and I think maybe 118 is being debated as to which name they're going to use, and then 117 I don't think even has a proposed name yet. So there's some stuff down there at that last main chunk of the center of the periodic table that has no usefulness to it, we'll say. They're all radioactive. They all have like little tiny itty bitty minute half-lives, like 3 seconds or less. We're mostly going to focus on the 88 naturally occurring ones. Although I have seen a little bit of debate about that. I've seen a few textbooks go, oh no, there's 90 that are natural occurring. So I stuck with 88. This is the chapter, as we proceed through it, that will eventually get to the nomenclature rules. And yeah, we're doing it kind of different this semester because a lot of this is online. I still really, truly advise you to become super, super familiar with the abbreviation versus name combination. Most of them are 1 and 2 letter abbreviations. There's that couple at the bottom of the periodic table that have like 3 letters because they're the ones that are still under debate. Talk about some of the most common ones for a moment here. When I went through this way a long time ago, if you kind of look down the letters on the left-hand side there, it kind of almost looks like it spells the word chomps. And that's, call it the brain trick, for remembering the 6 most common things from living systems. Now, granted, if you're talking about, rocks and inorganic things, there's a whole lot of other elements to choose from. But if we're building people, amoebas, plants, my cat, we're mostly going to have those 6 as kind of the overwhelming majority of the elements contained. Note, all of the ones there happen to be ones that have a single letter abbreviation. We got carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. For these 6, you will also notice that I will call it they match. The letter that is the symbol actually makes sense when it corresponds with the name of the full name. That's not always true. So we're going to back up a little bit, about 2,500, 3,000 years, spend a couple of minutes talking about some of the background that sort of led to modern day chemistry. So let's go back to the golden age of Greece. So we're talking about 500 BC, thereabouts. 2 guys, Democritus and Leucippus. Although I read an article recently, yeah, I know I read really weird things, that talked about there was a debate as to whether Leucippus, who was supposedly Democritus's teacher, was actually a real person. The idea there being that somehow there was a debate. Okay, hang on. My screen is doing something really strange here. What did it do to me? Okay. And somebody pinged me that said that there was somebody waiting to join. I'm trying to figure out how to activate that. Oh, I don't know. I don't see. where that went. Hang on, technical problems here. I'm trying to figure out how to admit somebody after my screen already shut down that part of it. All right, let's try this again. All right, so back to my Greek dudes. So anyway, there was a discussion as to whether Leucippus was a title or whether it was actually a guy's name. So I was actually fascinated by that. I ran across this, so I was looking for something else. However, okay, two Greek guys, obviously they speak Greek. This is way back when science and philosophy were kind of, sort of the same thing. Because, I mean, no tech, okay? A little bit of math, no tech. So they came up with this idea that everything in the universe was made out of small, and note the word is not invisible. The word is indivisible, meaning it can't be cut. And they dubbed them atomos. Okay, so part of this obviously should look really familiar because we've got atomos. Well, if we drop the second O, we actually get to see the fact that it is essentially the word atom. So this is where they came up with the whole atom idea to start with. But of course, they were stuck. They were seriously stuck. We've got this brilliant idea and no way to prove it. So let's jump ahead about 2,000 years. 17th century, so 1600s. Alchemy was the big deal, okay? And alchemy was, like I said, it's kind of a religion-ish thing, kind of magic, but there was actually some real data being churned into all of this. And if you were an alchemist, your big goal in life was, let's turn lead into gold, which actually can be done, okay? You need a nuclear accelerator and about 30 terawatts of power, and that will allow you to make about 20 atoms. So it definitely isn't cost effective, but we can do it. So why are they even remotely important other than the fact that, you know, they had this really crazy idea? Well, the problem that this ties into is, okay, think about the time period. 17th century, probably maybe 3 or 4% of the population can read and write. Everybody else, they're illiterate. So they were the scholars of their days. And hence, time period, most of the people who were alchemists spoke Greek and Latin. And as the 17th century began to head into the 18th century, we're also going to toss German in there too. So again, this gets back to the why is this important? So because we have people who are educated who are not necessarily English speakers, they used Latin and Greek and a smidge of German to name the things that we're later now calling elements. So let me pull up my list here. Okay. So we've got stibium. Okay, that's the Latin name. We don't call it that anymore. We call it antimony. But if you look up antimony on the periodic table, we kept a little snip of that Latin history because antimony has a symbol of SB. Cuprum. Okay, it's copper. We kept the Cu part for the symbols. Hydrogyrum, which is mercury. We use the Hg. Kalium, so that's potassium. We kept the K part. Argentum and aurum, silver and gold. We have Ag and Au. So more ridiculous trivia to like make these things stick in your brain. So James Bond has a archenemy whose name is Goldfinger. Well, in one of the movies, and actually in the book, they do actually tell you what the guy's first name is. And his first name is Auric, A-U-R-I-C. So in the world of literary humor, you could say that the guy who wrote that is sort of giving you a little bit of a pun on using the Latinized version of the name for the guy's first name and calling his last name Goldfinger. We've got natrium. We kept the Na. We now know it as sodium. Now here's where the German one comes in. Wolfram. Back before LED light bulbs, back before compact fluorescent light bulbs, we had incandescent light bulbs. They had a filament in them. And the filament was made of tungsten. We kept the W as the symbol. So this is a good collection here of some of the most common ones where when you look at the name, the English name, versus the symbols that are used, they look like they don't match. This is the Y, okay? Knowing the Ys is often helpful for helping kind of get a grip on more complicated information. We're gonna jump forward 20 years or so, talk for a moment about Robert Boyle. He lived in the mid-1600s, so middle of the 17th century. Some people will call him technically the first real chemist. He had a thing for air pressure. He did a study, partly at the base of a mountain and partly at the top of a mountain, figuring out that there was a difference in the air pressure. And later we'll get around to having a gas law named after him in a later chapter. So let's jump forward about 100 years this time. We've got mid to late 1700s. So this time we have a French guy. His name is Antoine Lavoisier. He liked to set stuff on fire. However, one of the things that is true here is he came up with the first really decent explanation on combustion. I mean, okay, you set stuff on fire, it burns, and you have ashes. He actually did things like collect the ashes, but also collect the gases that were put off when things burned. So he is the guy who gets credited with law of conservation of mass. And we talked about this just a little bit back in chapter 1. Mass is neither created nor destroyed. You only get to rearrange it, okay? You can't make it or break it. All you get to do is rearrange it. Well, he had a buddy who was, I don't know, we're talking about 10 years later or so. His name is Joseph Proust. So we're actually kind of heading into something that might pass for real chemistry at this point. he came up with this thing called the law of definite proportions. So a given compound always contains exactly the same proportion of elements by mass. So think about this, okay? But this, remember, we have a little bit of tech, but not a lot of tech. You have a water sample that's rain. You have another water sample that came from a well. You have a third sample that came from the ocean. But the water part of all of those samples has 2 H's and 1 O. The beginning to grasp the idea that these things were actually kind of truths about the compounds that were being studied, this was kind of a big deal because, like I said, little bit of tech, not a lot. So John Dalton, in some ways, did some of his own work, but he also stole from a lot of people too. He took Proust's idea and he took it a little further. Okay, and if you read what's written there, we've got 2 elements form a series of compounds, and the ratios of the mass of the second element combined with 1 gram of the first can be whole numbers. Okay, you kind of go, what? So basically, think about how we write molecules. We write element symbol, number. Element symbol, number. Sometimes there's parentheses involved. This is heading in that direction. It's the idea that, okay, if water's H2O, what happens if you have H2O2? Not something you would want to drink because it's hydrogen peroxide. This will eventually tie back into, I'm going to drop this term here, empirical formula. Empirical formula, we're going to do calculations with eventually. So in the world of science, publish or perish has kind of always been a thing. Even though Dalton really wasn't the originator of a lot of these ideas, he wrote a paper about it. Therefore, he kind of gets credit for it. So he swiped one idea from Democritus. And of course, he took out the second O there. And every element is made of tiny particles named atoms. Then he kind of went, okay, well, let's think about the whole idea of same and different. All atoms of a given element are identical. Now remember, we're back in this era when tech is really pretty low. You've got balances, you've got glassware, you have microscopes, kind of sorta. Leeuwenhoek and all of his thing. But there's no electron microscopes, there's no electrical equipment. So this is kind of a big deal. We've got the whole compounds are made when the atoms combine idea. And you can predict relative numbers and types. And then he stole a bit from Lavoisier and kind of restated his version of the law of conservation of mass. He also kind of sort of made the first periodic table. He had a bunch of mistakes in it. There's a bunch of things that he stuck in the wrong place compared to what we know now. But he did actually get a fair bit of it right. So it was a good starting spot. I mean, again, we're talking 1700s here. So about the time our nation is saying, yeah, we don't want to belong to England anymore, people are beginning to make some fairly significant steps forward toward modern day chemistry and modern day physics. All right, let's go a little closer to modern day.
Quick question.
Yes.
A textbook is saying that Dmitri Mendeleev is credited with.
He's not the first one, though.
No?
He's the one who got it closer to right.
Oh, okay.
He got it
moved
closer to
along.
right. Okay.
Okay.
Dalton started it, and it didn't really even look like the periodic table that we have now. Okay, it was organized differently. Mendeleev organized it a lot closer to the modern day periodic table, and he still had some errors too, because there were a few things that he stuck in like the wrong columns. So it's a stepping stone process. Mendeleev is the one who had the closer version, but he wasn't exactly the originator.
Okay.
So we've got atoms, stick them together, we make compounds. Okay, we've kind of sort of got a grip on that at this point. We're talking 1700s here, and then we're gonna leap another 100 years into the 1800s. One of the things that they began to discover is that you had the possibility that atoms weren't the be all to end all, that maybe there was actually something smaller. And I am going to try to do something different and share a Google picture. I can find the one I want. There are some pictures of this in your textbook. All right, let me hop back over and see if it'll let me do this. All right, share and go down. Why is it not showing that? I can't get it to show my other picture. Oh, well, drat. Okay. That annoys me. Anyway, in your textbook, there are pictures of J.J. Thomson's cathode ray tube. Okay. Remember back before we had flat screens? We had big, deep TVs. Those are cathode ray tubes. Okay. Granted, they're a little more advanced than what he was dealing with, but it was same basic idea. And so he plugged it in. He looked at this little negative particle stream, okay, and it hit the opposite end of his tube, and it glowed. Okay, so he began to rationalize that since one end was negative and one end was positive and they were going toward the positive end, well, they must be negative because he knew opposites attract. And he did all sorts of other things too. He stuck some things in the way of this little stream of particles. And he found out that they had the ability to cast shadows, that they had the ability to be bent in different directions. So he essentially is responsible for the whole electron idea. So remember Lord Kelvin? Remember I said we were going to see him again? Okay. He had this idea that was sort of based on partly on the idea that we have these electrons, but he also knew that we had positive bits too. So remember, he's a British dude. Okay, so he's like going, well, let's stick it all together. Kind of looks like a plum pudding. Okay, if you don't know what a plum pudding is, think fruitcake you set on fire. Okay, which is about the only thing it's good for. It didn't have any organization to it. You just had this wad of positives and negatives that were all kind of jammed up there together. And that's what he thought. it's like, okay, this works, you know, this it fits the criteria. So now we introduce Millikan. Okay, so he's going to expand upon the electron idea. He does some little calculations with some oil droplets. He figures out the magnitude of the negative charge. Relevant, okay, important, contributes to the big picture. About another decade pass. It's a guy named Ernest Rutherford. Ernest Rutherford is studying radioactive things. Specifically, he's studying things that emit alpha particles. That's a type of radiation. Alpha particles are positively charged. So he has this big block of lead, and he puts his little piece of radioactive gunk in the block of lead, but there's a hole drilled in one side. There's pictures of this in your textbook. And he looks at where he's sort of aiming the alpha particles. Basically, he's kind of, he created a gun. He created a radioactive gun, more or less. And he aims it at a little piece of gold foil. Gold is kind of cool. Gold is something that if you pound it really, really, really flat, you can get it to be about 1 atom thick. And you can eat it too, just more trivia. Ever go to a like really expensive wedding, okay, and they have like gold leaves stuck on their wedding cake, and you can eat them, okay? Gold just passes through your system. So anyway, he's shooting his little blips at the gold foil. So think about this, okay? Think about like going to the firing range and you're shooting bullets at a paper target, okay? Obviously, you expect your bullets to go through the paper target and hit the, you know, the backstop and all that kind of thing. So that's what he was expecting, because the alpha particles are little and the gold is this flat sheet of messiness, okay? Because remember, plum pudding theory. And he didn't get what he expected, okay? Some of those alpha particles started bouncing back. Some of them bounced out at angles. Some of them bounced almost straight back from the direction they came in. So he and Kelvin were buds, okay? He wrote a letter to Lord Kelvin. He said in his letter, it was kind of like firing a cannonball at a sheet of paper and having it bounce back. That's how sort of astounded he was at what he had seen. Now, why is any of that sort of relevant other than it's interesting to watch? He proved that the whole plum pudding theory, yeah, that didn't work, okay? There's a big glob in the middle of your atom. We're going to call it the nucleus. And all those little electrons, they kind of orbit, okay? Think itty-bitty solar system. Granted, this is not entirely correct because eventually we'll talk about the refinements of this. That's another chapter. But we've got this nucleus, big, dense center to your atom. So let's think about size, okay? If you have the nucleus in the middle, and I did this in centimeters because that was the easiest thing it seemed to find a reference for. The diameter is 10 to the negative 13th centimeters. So take a 1, put 12 zeros out in front of it, okay? We know that the nucleus has actually 2 things in it. We know that the nucleus contains protons and neutrons. Now, electrons are smaller, as well as being negative. Now look at the exponent, okay? We had 10 to the negative 13. That was the exponent that went with our nucleus. We have the electrons flying 10 to the 8th centimeters away. Now think about this from an order of magnitude point of view. We're talking zeros here. That's 5 orders of magnitude difference. So I gave you a little bit of a real world comparison here. If your nucleus was the size of a grape, the nearest electron would be about a mile away. So I saw a magnificent bumper sticker a while back that the chemist in me appealed to that says, be humble. 80% of you is water, and the rest is empty space between electrons. And I thought that was really hysterically true. So that's kind of where we're going to end tonight so that we can pick up with talking a little bit more about neutrons and protons and electrons on Thursday. And then we are going to get into atomic numbers and atomic masses and deciphering a little bit of the information on the periodic table. So we're a little ways into chapter 2. Homework for chapter 1 is due on Thursday. I will go back and update on Canvas and put the 3rd of September in as the due date. So anytime before midnight, you could submit it. Like I said, I won't grade it till the weekend.
This Thursday, right?
Yes, this Thursday.
Okay.
So hopefully, if you haven't finished it, hopefully you have begun working on it. You still have a couple more days before it actually needs to be turned in. So we've done chapter 1. We're a little ways into chapter 2. Chapter 2 is a little less all over the place compared to chapter 1. Periodic table stuff will kind of develop into organization of the periodic table, and then the whole end of the chapter leads into learning the rules for nomenclature. It is very much like learning a foreign language. When you learn a foreign language, a lot of times you learn the nouns as kind of like the first thing, because think like if you're like little kids, okay? Little kids, it's like you touch things and go, ball, apple, mommy, daddy. A lot of times when you're learning foreign languages, you learn concrete objects first. That's kind of what the element names are. But then as you progress in a foreign language, you begin to conjugate verbs. So once you start sticking elements together, some of the endings are going to change, and some of them are going to develop extra kind of parts to them as you assemble them into actual molecules. So we'll kind of head in that direction later in the week. Other questions?
When is the dry lab due date, and how we submit it again?
So dry lab 1,
yeah,
which is roughly concurrent with experiment 1, for the group A people, it is due on the 21st of September.
Mm-hmm.
Okay. Since the group B people should be working on the dry lab 1 over the next week or so, such that when you come to do experiment 1 on the 14th, that means everybody will be done by the 21st. So the group B people will be turning it in the following real-time face-to-face, which actually is probably the 28th.
Oh, you got time.
I have to wait. The way it has to work is I have to wait till each pair of labs is done, and then have that group of people see me the next time. When we get to the end of November, things become more complicated. But at the moment, the way the schedule works, barring the Labor Day thing, people who have me for lab see me every 2 weeks. So when you come to lab each time after the first time, you will then bring 2 completed labs to me the next time. a dry lab, and a wet lab. I know it's kind of messy, and it's the best we can come up with right at the moment.
Not the best way to study chemistry remotely.
Yeah, we're fumbling in the dark, that's for sure.
If we've submitted the homework already, now I'm pretty certain I submitted already with some of the answers and significant figures, but I did show all my work. Is that something maybe I should go back and rework and then resubmit?
No, that's fine. If you did in significant figures, that's fine. I'm only going to look at the significant figures specifically on the ones that ask for.
Gotcha. Okay.
When we do significant figures, we use only the rules that you give us in the notes, right?
Yes.
Because there are some more rules that I find on YouTube, but I guess you don't have to use them, right?
Not everybody who talks about them on YouTube utilizes them the same way, which is part of the problem. We are sticking more or less to the rules that are given in the textbook.
All right, that's cool.
And as far as rounding goes, any calculations that are made in the process of achieving the final answer, it made sense to me that you don't do any sort of rounding until
you get to the
final.
end. Yeah.
All right.
Like
Excellent.
drag a whole bunch of digits with you. Once you get to the end of the problem, then round it to have the appropriate sig figs.
Okay.
Yeah, that's true.
All right.
Other questions on homework or lab?
Will you mark us wrong if we're like 1 decimal point off? Like if it's like 0.2 instead of 0.3?
Only if it says give the answer in sig figs.
Okay.
I am not in your lab class.
Okay.
I'm in the McHugh one.
Right, a Wednesday?
Yes.
Okay.
AKA tomorrow night.
Yes.
And do you know if there's just an across the board way that you guys are assigning group A and B? Because I've gotten nothing
it was
yet.
random. It was really
Okay.
random. I don't know if Dr. McHugh has a method, but as far as I know, because a lot of us started out going like, okay, took our roster and just went every other person, okay? But then we had drop add. If you, like, the people who have me for lab will probably have noticed that I updated that little chunk of the syllabus like 4 times over the past week, because every time somebody dropped and somebody else added, I had to tinker with the groups. It's been kind of a random event. We just divided the class in half.
Okay. Because we haven't gotten them yet. I sent an email, but we'll see what happens.
Oh, I'm surprised. Because I saw Dr. McHugh briefly, for real. He actually came by my lab last night, and he and I talked for a few minutes, although we didn't talk about lab groups. I'm surprised. I'm surprised that he didn't send that out today.
Yeah, I have the email open. I was hoping I'd see something before I asked you, but there's still nothing.
Yeah. As opposed to email, you might double check your Canvas shell, because that's where I put the list. I put the list as part of the shell, as opposed to doing individual emails. And I just like listed by last names. Just, here's the 10 or 11 people, here's the 10 or 11 people, and A, B. So yeah, I'm surprised that he didn't actually send that out. So, but I would double check the Canvas shell.
I'm checking it again now, but we'll see.
Yeah, I don't know. I don't even know the exact number of people that he has registered for that lab. I have 22 names on my roster right at the moment. we can't have more than 24, okay? Because even if this was a normal average regular semester, OSHA only allows us to have 24 people in lab at one time. So current rules, we get to have half that much, which is 12. So we can't have more than 24 people in his lab, but I don't know actually how many he has in lab.
Yeah, I'm not seeing it in the Canvas shell. I was also hoping if I asked you, maybe someone else participating in our class that also has McHugh might have like seen something that I didn't, but
Yeah, I don't know.
that's all right. Well,
I wish I had it. There are so many complications with this particular semester in terms of communications, of us trying to problem solve all the things we didn't kind of anticipate. Yeah, it's I have hopes maybe he'll send them out tonight or tomorrow morning, because the Wednesday lab I think is at night. I think it's at 5:30 to 8:30 the way mine is.
yes, ma'am.
So I have hopes that maybe he will send it out.
Sounds good.
Oh, somebody else said Dr. McHugh commented that he had not made out up the list. Maybe he's going to send it out tonight.
Awesome. Thank you, Kevin.
He's been having some connectivity problems, which is part of the reason he was in the building last night when I was in lab. He said he'd been having connectivity problems at home, and that he was experimenting with the idea of trying to stream using the internet in the chemistry building. So, yeah, I don't know. I'm lucky. I have FiOS, okay, here in my house. So I actually have really good internet connectivity here.
Well, thank you for
Okay.
entertaining
Other
my
questions
question.
regarding lecture or lab that I can maybe try to answer?
I have two
Otherwise, I will
offhand,
see. Excuse me?
two
Okay.
offhand questions. Really, they're just more points of curiosity. So the cathode ray tubes, isn't that the same similar setup that they use to test like metamaterials, materials that they can bend light around? They have two nodes.
I have no idea.
Oh, okay.
Yeah, I have no idea. I've never seen that particular usage.
Yeah, they literally use the electrons to bend light around materials. I just was curious if it's something I heard about. I was curious if that was the same kind of thing they used.
Yeah, I'm sorry.
Or
I don't have an answer
visibility.
for that.
No. Okay. And then just on the thought of talking about atoms not being the smallest particle, what is? I've heard of quarks, and then of course there's the movie Ant-Man, and you can imagine how small things get there.
Current quantum physics theory uses the quarks. There are 6 quarks. There are top and bottom, up and down, strange and charmed. Sounds like they were doing good drugs when they named these, but that's actually what they're named. I actually really like quantum physics, so I actually know a fair bit about that particular topic. But the current accepted theory is that quarks are the smallest. They
Do
are
they even
supposedly the bridge between matter and energy.
Do they have a charge or no?
That's hard to answer.
All right.
Once you get to that level, they don't have a charge. They have a spin. And when you combine them in 2s or 3s, you can then create charges. If you're curious about that sort of thing, I have a name to give you. There's a guy named Michio Kaku. Okay, Michio is his first name. Kaku. He is a Harvard professor who has written a series of books that have we'll call it minimal math that are about quantum theory and hyperspace and Kalebaya, 11 dimensions, and a whole bunch of other related things. I have a whole handful of his books. I think he's really amazing. You might find them interesting. I think he also has some YouTube videos.
I was going to say, is it written in layman's terms?
Like I said, it has not a lot of math because the normal discussion mode involves a lot of tensor calculus. Okay, his books don't really have much math in them. I don't know whether I'd call it layman's terms, but it is a much simpler version than full-on quantum physics.
That'd be interesting to look at.
So I'm really fond of him. He's one of the best writers out on the market today for that topic. There's some other ones too, but he's the one that most notably comes to mind.
Okay. Yeah, it's just a point of curiosity. Thank you.
Other questions? All right. I will see, hopefully, all of you on Thursday.
Have a good one.
Bye.